Introduction to spectroscopy. Spectroscopy is a very vast area, but proper understanding of the electromagnetic radiation and the spectrum of rays belonging to the electromagnetic radiations is very important. Why? Because each area of electromagnetic radiation has to contribute something to molecular structural determination, and that is the advantage of using various regions of UV region, visible region, IR region, radio frequency region for different types of molecular structural detailing. And it is the beauty that each one contributes only a part of information about the molecule. So, let us try to understand what spectroscopy has to offer. We have been referring to very important two techniques in analytical chemistry. One is the chromatographic technique and the other one is the spectroscopic technique. The chromatographic technique is responsible for the separation of complex mixtures, so that individual compounds can then be analyzed on spectroscopic methods. If we try to look at the various forms of energy, and particularly with respect to light, it can be explained by wave theory or by particle theory. Two-dimensional form of electromagnetic radiation, plain polar electromagnetic radiation travelling along an x axis. So, it is debatable whether the energy or the light is in form of a particle or a wave, but nevertheless we still consider it as a wave. The wave is characterized in three ways as shown in the above figure. It can be described as a wavelength, that is the difference between the two humps, or it is described as wave number, that is the number of waves in unit length or distance per cycle, reciprocal of wavelength. So, if we say wavelength, then it is the reciprocal of wave number, or it can be expressed in terms of frequency nu is the number of collisions of the field per second, that is expressed in hertz. It can also be expressed in terms of velocity c. Independent of wavelength, in vacuum the velocity of light is considered as 3 into 10 to the power 10 centimeters per second, or it can again be called as photon or quanta. Quantum mechanics nature of light to explain the photoelectric effect is where the photon term is used. Most popularly we talk about the wavelength or the frequency. The wave number, the velocities are not so frequently used when we are referring to different radiations of electromagnetic radiation. Now, if you try to look at this particular slide, you will see that the areas are very clearly demarked. The X-ray area, the gamma ray area, the UV area, and you see a very small visible region which has been expanded at the bottom, and then next to the visible region is the IR region, then comes the microwave region, then comes the FM radio waves and the AM radio waves, and furthermore are long radio waves which are responsible for the NMR analysis. So, you see that the entire spectrum, as I mentioned a little while ago, different regions and their energy or their wavelength are having certain properties which can excite only some part of a molecular structure, and therefore imparts information only about that part. So, X-rays will give inner bonding and crystal lattice structures information, UV will give information related to unsaturation in the molecule, IR will give information related to the functional groups that are present in a molecule, and so on and so forth. Now, what is meant by the term spectroscopy and what is a spectrum? It should be clearly understood. Spectroscopy is a technique that uses the interaction of energy with a sample to perform the analysis. So, the technique is called spectroscopy, and the data that is obtained from the spectroscopy is called spectrum. A spectrum is a plot of intensity of energy detected versus the wavelength or mass or momentum or frequency of the energy. So, spectrum is the graph that is obtained out of this spectroscopic analysis. Now, this is a very interesting slide where I want to draw your attention to see how the interaction of electromagnetic radiation can really affect our day-to-day life and our molecular structures and in molecules that we deal with in day-to-day life. And it is measured by the characteristics and the properties and the quantity. See, radio waves are responsible for FM, radio waves are also responsible for NMR. Microwaves are responsible for different types of digestion processes that I had covered a while ago, and they are also used in domestic purposes for baking cakes. Infrared is a region where we get functional the thermometers and different types of infrared heating devices are made out of it. Visible region is what we can see. Ultraviolet is related to sunlight. X-rays are related to the X-rays that are taken for broken bones or even intact bones, and gamma rays, of course, we know are used in different other purposes. So, this was just to give you an overall idea how spectroscopy even plays a very important role in our domestic life. Now, when we try to look at the spectroscopy and the relationship between them, the wavelength is directly proportional to the frequency, and when we try to find out the sign of proportionality, it is always replaced by a constant, and here c is the velocity of light. So, lambda, which is the wavelength, is equal to c by v, and the units of wavelength are normally angstrom, which is 10 to the power minus 10 meters, or 10 to the power minus 9 if it is nanometer. If it is micrometer, it is 10 to the power minus 6 meters. So, these are certain relationships which I wanted to make it very clear to you, because time and again we will be referring to angstroms or nanometers, and one should know where does it stand in a meter scale. Now, light energy could have a longer wavelength, but that longer wavelength light will have low energy, or it may have shorter wavelength and light will have higher energy. The De-Broglie relationship link between particle and wave behavior should also be understood, because whether it is a particle or a wave must be understood very clearly. E is equal to h nu, where h is the Planck's constant and it is also a sign of proportionality, or when we can say that nu is c by lambda. So, it can be substituted that E is equal to h c by lambda. So, these are different relationships of energy with Planck's constant, with velocity of light and wavelength and frequency. So, how they are interrelated must be understood. The De-Broglie relation with the E is equal to mc square is also very well known. Combining the previous equation, that is C is equal to mc square, that will be equal to hc by lambda, or that gives that lambda is equal to h by mc. So, these are different types of energy, mass and wavelength and velocity of light, Planck's constant, how they are connected to each other. This gives De-Broglie's relationship, gives this equation very clearly. Now, when we look at the different regions of electromagnetic spectrum, we see that radio frequencies are responsible for the NMRs. Similarly, the microwave is responsible for the rotational power of a bond. Then comes the far infrared, infrared and near infrared. They are responsible for causing vibration in a bond. And similarly, the visible and the ultraviolet and the vacuum ultraviolet are responsible for the electronic excitation, that is pi to pi star or n to pi star excitation of electrons are brought about by these particular electromagnetic radiation areas. Then comes the X-ray, which excite the inner shell electrons, and then comes the gamma rays, which are which cause nuclear reaction and give out alpha, beta, gamma rays. So, that is how the regions of electromagnetic spectrum are divided, and each area contributes to its particular functioning. Now, when we try to look at electronic distribution in an orbital, the sigma and the sigma star and the pi star orbitals look like this. Molecules, when they are radiated, what exactly happens? When molecule is excited with h nu is an energy source. What exactly happens to that? It forms m dot, that means it is in a excited state. The mass has now become excited. Change in nuclear energy level, X-rays are very high. Change in nuclear spin state, lower energy and causes magnetic field. Radiation excited species have a lifetime of 10 to the power minus 8 to 10 to the power minus 9 seconds. So, what it happens that this excited molecule either gives then the normal molecule and heat by collision with the neighbors, or it may give h nu by emission, highly probable at high frequency. So, it can either give some heat and come back to its normal state, or the excited molecule, that is the m star, will give some, it will emit some energy. Now, these are certain molecular electronic transitions that are permitted. So, you will see that from the transition of pi to pi star, it is the most facile energy exchange that can occur, or n to pi star, but n to sigma star or sigma to sigma star requires the highest energy. So, depending on what kind of UV light is shown on the molecule, the most facile exchange or the most facile excitation would be pi to pi star, whereas the next facile exchange would be n to pi star. However, n to sigma star or sigma to sigma star requires still higher energy. Now, energy transitions, that is sigma to sigma star, observed only in highest energy, that is vacuum ultraviolet, rarely never observed in the normal UV and visible range, whereas n to sigma star, saturated compounds containing atoms with unshared electron pairs, that is non-bonding electrons capable of this transition. This transition requires less energy, happens in 150 to 250 nanometer range, and the absorption below mostly 200 nanometer is what is observed. The molar absorptivity are fairly low, that is 100 to 3000 liters per centimeter per mole. So, this is why these two transitions, energy transitions, are not so popular when we are talking about electronic excitations. Adsorption maxima of certain solvents are given here. You will see some examples of adsorption due to n to sigma star transition has been shown here, and water particularly, which absorbs at 167 nanometer, having a lambda max of 167, shows a molar absorptivity 1480, whereas methanol shows lambda max at 184 and molar absorptivity at 150. Similarly, methylene chloride shows a lambda max at 173 and has a molar absorptivity at 200. Idomethane shows a lambda max at 258 and has a molar absorptivity at 365, and so on. One can go on looking at the list and see that the lambda maxes are much lower and the molar absorptivity of diethyl ether is very high. Otherwise, most of these compounds have very low molar absorptivity, and these are typical examples of N to sigma star transitions, which and the samples are all taken in vapor state. Energy transitions which are more popular are the N to pi star and pi to pi star, and they have molar absorptivity which are in the range of 10 to 100 liter per centimeter per mole, and therefore, pi to pi star is still more popular, which has a molar absorptivity between 1000 to 10,000 liter per centimeter per mole. Application of these two particular energy transitions are what we are going to study in absorption spectroscopy to understand the chemistry of organic compounds, and it is totally based on this transition to excited state of pi star. Energy required for those excited states is within 200 to 700 nanometers. So, it is well within the UV region. Chromophores involved are unsaturated functional groups to provide the pi orbitals. N to pi star transition are hypsochromic, that means they shift towards blue light with increasing polarity of the solvent, and pi to pi star transition is bathochromic, which shifts to red with increasing solvent polarity. Now, let me explain you a little bit about these things, because it is now getting a bit more complicated. What is a chromophore? A chromophore is a part of a molecule which has the pi and the N bonds and are in conjugation with single bond. When the double bond, single bond, double bond are in line with each other, one after the other, we say that the system is conjugated, and the more the number of pi bonds, the more will be the excitation of these pi electrons to pi star, or N electrons from the heteroatoms like nitrogen, oxygen, chlorine, sulfur, phosphorus and so on to the pi star. Now, these cause increasing of wavelength or decreasing of wavelength, and that is what is known as the hypsochromic and the bathochromic changes in polarity. When we try to look at the interactions of molecules with this radiation, it is very interesting to see that the energy levels can create different types of interaction. It can either cause rotational energy levels, or it can create vibrational energy levels, or it can finally cause electronic energy. Now, the rotational and the vibrationals are brought about by the IR energies or IR lights, whereas the electronic energy transitions, which are much higher in magnitude, are brought about by the UV light or the visible light. Energy level diagram associated with absorption of electromagnetic radiation, that is, the rotational changes are shown by the far infrared region, the rotational vibrational changes are shown by near infrared region, the rotational vibrational electronic transitions are given by the visible and UV regions, and therefore, from the electronic ground state to the electronic first excited state are depicted by E0 and E1. So, you can get a relative idea what are the energy contents, whether the IR energy is stronger than the UV energy. The immediate answer will be that IR energies are only causing rotation or vibration. So, they are smaller in their energy content, whereas the UV lights excite the electron from one level to another orbital, and therefore, they have larger energy content. Miscellaneous information that is related to conjugation. Little while ago, I was talking about single bond, double bond, single bond being in repetition. Now, when such a system exists in a molecule, then we call it that the molecule is conjugated or the system has conjugation. Electrons in that are delocalized. Lower energy is required to excite electrons. Absorption maxima will shift to longer wavelength. That means, because I just told you a while ago, longer wavelength, shorter energy, shorter wavelength, higher energy. So, that should be kept in mind. If you keep one in mind, the other one will be automatically remembered. But if you try to remember both of them together, there is a possibility of mixing it up. Now, you have already understood what are chromophores, but what about understanding another additive which is called oxochrome? Oxochrome on their own do not impart any color contribution. However, they help in the conjugation process. If a functional group that does not absorb radiation by itself in the UV range, but has a shifting effect on the main chromophore peak to longer wavelength as well as increasing their intensities. For example, like hydroxy group, it is not absorbing by itself, but when it is in conjugation with a double bond or other such conjugated system or NH2 or benzene chromophore, then they act as on the benzene chromophore, they will act as oxochrome. Inorganic ions, a number of inorganic ions exhibit UV absorption as a consequence of pi to pi star transition. For example, nitrate will show or will absorb at 313 nanometer, whereas nitrite absorbs at 360 and 280 nanometer. Carbonate absorbs at 217 nanometer, whereas azide absorbs at 230 nanometer, whereas trithiocarbonate absorbs at 500 nanometer. So, you see that different types of inorganic ions have different wavelength because they absorb differently and because they have different types of oxochromes attached to the main chromophore. Quantification for spectroscopy. Now, this is the most important part of the spectroscopy. Why? Because this is the crux what happens in a spectroscopic transformation or data collection. Either we consider transmittance, that means the fraction of light that is incident and the fraction of light that is transmitted are compared. That is called transmittance. Or it can be a light is incident, it absorbs and then it transmits the light which is slightly less in its energy. Now, a part that the amount of incident radiation which has been absorbed by the medium is expressed as log 1 by T or is equal to minus log T or is equal to log PO by P. Beer's law, Beer's, Borger's, Lambert's law, radiation energy decays exponentially and T, that is the transmittance, is always proportional to P over P0, and therefore, it is to be understood that it is proportional means whatever be the molecular species concentration, only that much will absorb, and therefore, it is a method of quantifying these substances, because the number of species, the concentration is related directly to its absorption energy. Quantification, if we present in logarithm form, log t is equal to log p by p 0 is equal to minus kb, the same stands for concentration, that is log t is equal to log p by p 0 is equal to minus k prime c, or A is equal to k prime c, or A is equal to a b c. Now, what are these A and B and C? The small a is the proportionality constant of absorption, and B is the path length of the method or the medium. Now, path length, that means how much light is being shown, is also very important, and therefore, it is expressed in moles per liter. C is expressed in moles per liter, and path length or cell length is expressed in centimeter. Then the small a or the molar absorptivity has the special symbol and the units are liters per mole per centimeter. The molar absorptivity range for UV visible is 0 to 10 to the power 5. So, it is as low as 0 and it can be as high as 10 to the power 5. When we try to understand Beer's-Lambert's law, we also have to remember that these molecular species are not interactive among each other. Each species is an individual, and that individual species is absorbing light, and the absorption is directly proportional to the concentration of the material. But sometimes when these molecules are in aggregates, the Beer's-Lambert's law will not hold good. There is deviation from its direct proportionality, because it is only valid at concentrations usually below 0.01 molar. If the solution is very concentrated, it may not have that complete effect of its reaction, and each entity will not be just one entity, but will be an aggregation of more than one entity. Molecules interference. Distance between molecules affect charge distribution of molecules, particularly in the case of ions. Effect of relative index. Concentrations affect relative index, and therefore, molar absorptivity is affected. So, either it will be low or too less, or it becomes the linear graph is no more linear. It then takes a turn, and that is not considered as one of the best methods of analysis, because for any law to be valid, it is important that the graph or the calibration graph should be a straight line passing through the axis, and the axis is the point where the y axis and the z axis actually collide. So, this 0, it should be passing through the 0, and one axis gives the absorbance, the other axis gives the concentration, and that is what shows the proportionality between the two. But if the solution is very concentrated, if there are molecular aggregates, then this proportionality will not hold good. Beer-Lambert's law also faces challenges when there are chemical deviations. Either the molecule is associated or dissociated, and the reactions take place within the solvent, with the solvent and other molecules, like in buffered solution or unbuffered solution, then the instrument will not show correct data. Why? Because the Beer's-Lambert's law is not holding good. So, one has to keep in mind, first thing, solutions should be very dilute. So, they are fairly apart, there should be no association, no dissociation or reaction with any kind of solvents or other molecules when the analysis is being carried out. Instrumented deviation, monochromatic radiation, quality of monochromator and control of bandwidth and slit are other parameters that need to be considered. Instrumental noise, accuracy of measurement of transmittance, quality of detector also should be very good. If these have little bit of discrepancies, or if the instrument shows any kind of deviation, or if the instrument is not regularly calibrated, or if the quality of monochromatic light is not good and the bandwidth and the slit are not maintained at the right parameters, then also the Beers-Lambert's law will not hold good. Atomic and molecular spectrometry. This is what we are going to study in this whole chapter of spectroscopy. What happens to a molecule when it is subjected to electromagnetic radiation, or what happens to molecules when they are subjected to electromagnetic radiation. Atoms behave slightly different way. We just saw when we were doing atomic absorption spectroscopy, that came under the category of atomic spectroscopy, whereas molecular spectroscopy is where we are looking at the entire picture of the molecule. Transitions between energy levels may occur in several ways, providing different types of spectra for analysis. So, molecular spectrometry is much complicated as compared to atomic. The intensity of the spectral emission or the reduction of intensities by absorption is related to the concentration of the species producing the spectrum. So, when we try to look at the intensities of the spectrum emission or reduction of intensities by absorption, so it will be either emitted or absorbed. These are the two things that happen when electromagnetic radiation is shown, and that will produce a different type of spectrum. Certain transitions are favored by quantum theory rules. Why? Because energies are quantized. It is not that by putting some energy, some excitation will take place. Only excitations which are matching will cause or the energies when they are matching with the molecular part or chromophore will only show excitation, not otherwise. Transitions for a given set of energy levels defined as quantum numbers, there are several possible types of transitions, but only several possible types. If energy is supplied by passing electromagnetic radiation, the molecule may absorb energy and may get promoted to higher energy level. So, it is possible that if the energy levels are matching, then only this absorption will take place, and therefore, if energy is supplied by passing electromagnetic radiation, the molecule may absorb only when it is compatible and may be promoted to higher level, because it is rightly matching with the kind of energy that is required for pi to pi star transition. If the molecule is activated thermally and then it gets promoted, it would emit energy in falling back to the lower level. So, obviously, if a molecule is heated and then it is thermally excited, then it will give out that heat by emitting that energy and come back to its natural position. Let me tell you one thing, that molecules always want to be at a peaceful situation. So, whenever they are excited, either they have to emit or they have to absorb, and so if they cannot keep this energy within themselves. So, this absorption has to be emitted in some form of the other. They may revert back to their original space by emitting, or they may give show that they are excited, and that absorption will be studied. Quantitative spectrometry. The word quantitative means it is an absolute value, a quantity is decided. In emission spectrometry, the intensity of the spectral line is related to the number of emitting species present in the emitting medium and to the probability of the transition. So, in emission spectroscopy, it is the intensity of spectral light will show that it is going to emit species that have been absorbed or excited or elevated to a higher energy level. In absorption spectrometry, the intensity of incident radiation is reduced, which is because it has interacted with the atoms or the molecule, raising them to higher energy. So, here what happens, that incident light has some energy and the light which is coming out has some other energy, but this is at a higher energy, this is at a lower energy. So, it is assumed that this loss of energy is what has been taken up by the atom. So, it is very quantitative, as much it will absorb as the concentration of these molecules or atoms are present in the medium. It cannot get lost, it cannot get added up, it has to be in sign of proportionality, and that is what helps us to understand the spectroscopic method. Coming to infrared spectroscopy, particularly that is used in organic chemistry, infrared spectroscopy, because here the light source will be infrared. It is the subset of spectroscopy that deals with the infrared region of the electromagnetic radiation or electromagnetic spectrum. It covers a range of techniques, the most common being a form of absorption spectroscopy meant to identify compounds. So, it should be understood that part of electromagnetic radiation or spectrum which deals with infrared region is what is the study of the present lecture. It covers a range of techniques, the most common being the form of absorption spectroscopy meant to identify the compounds only from the point of view of their functional group, whether an OH molecule, whether an OH moiety is present or not, whether NH2 is present or not, whether carbonyl is present or not. If the carbonyl is present, then whether it is aldehyde or ketone, or does it belong to acid carbonyl, or does it belong to anhydride carbonyl, is the study that will be understood through the use of infrared radiation. The infrared portion of the electromagnetic spectrum is divided into three regions, as what we saw also in one of the earlier slides, the near, the mid and the far infrared, named for their relation to the visible spectrum. The far infrared, approximately in the region of 400 to 10 centimeter inverse, lying adjacent to the microwave region, has low energy and may be used for rotational spectroscopy. Second, the mid infrared, approximately ranging from 4000 to 400. This is the one which is most popularly used, may be used to study the fundamental vibrations and associated rotational and vibrational structure, and therefore, these are regions which are of very great importance for knowing the functional group and its presence. And the third region that is important is the higher energy near IR, approximately ranging from 14,000 to 400 centimeter inverse, can excite overtone or harmonic vibrations. The names and the classification of these sub-regions are merely for convention, because they belong to different regions and they do different things in a molecule. That is why the information imparted by these groups is also very clear. They are neither strict divisions nor based on exact molecular or electromagnetic properties. Near infrared spectroscopy. Near infrared spectroscopy, which we will refer as NIRS, is a spectroscopic method utilizing the near infrared region of the electromagnetic spectrum from about 800 nanometers to 2500 nanometers. Typical applications include pharmaceutical, medical diagnostics, including blood sugar and oximetry, food and agrochemical quality control, as well as combustion research. So, you see it has a versatile area in which it can be used, and the information imparted by the near infrared spectroscopy can be so important that it can serve in the areas of pharmaceutical, medical diagnostics, including blood sugar, in the area of food and food chemistry, in the area of agrochemical quality control, and in the area of combustion research.